Thank you. Thank you very much for the warm introduction. It's an honor to be here and participate in this lecture series. I want to first clear up any possible misconceptions. I have one kid, just one, and he has one head. Okay. This two-headed thing was taken with Photo Booth on the iPad, and it's his favorite thing to do is to take pictures of himself with two heads. Okay. So anyway, that's impossible, and he's thinking about it. Okay, there we go. All right, okay. So, so I have two goals for this talk, and they're kind of conflicting in a little bit. So the first goal is I want to tell you about the state of the art in circuit complexity lower bounds, in particular areas of circuit complexity at least. And the second goal is to give a general talk for a scientific audience. So I'm going to try to navigate these two things, and hopefully it will turn out okay. All right? So let's begin. So as a young computer science theorist, one is taught that there are roughly two kinds of people. There are algorithms people, and there are complexity people. Okay? The algorithms designers asked the following very positive, upbeat questions. They ask, when can we solve problems quickly? What can we do with computers? When can we find a good algorithm? What does good mean? Good could mean many sorts of things. Generally speaking, it means that your algorithm is time efficient. It runs very fast. Okay? On the other hand, there's this other group of people called complexity theorists. Okay? The complexity theorists are negative Nancys. They ask, when are problems difficult to solve? Okay. When can we prove that a problem is not easy? Okay. In slightly more technical terms, when can we prove a lower bound on the amount of time that we need to solve a problem, or the amount of resources needed to be consumed in order to solve a problem? Okay. So this sort of lower bound thing versus algorithms thing is going to be pretty prevalent in this talk. So here are some intuitions about theory that you build up again as a young computer scientist. You learned that the algorithm designer and the complexity theorists have opposing goals and tasks. Okay, certainly the way I presented it, I mean, one is trying to say there's an algorithm, the other one is trying to say no. You know, so the way I presented it, they're really opposite to each other. Okay? And the second thing you learn, one way or another, that the algorithms tribe has an easier life somehow. Somehow, designing algorithms is just much easier than proving lower bounds. And this intuition is really, really strong. I mean, you want to say, look, if I design an algorithm, I just have to give you one piece of code that's just going to work and solve the problem no matter what. But if to show a lower bound, I have to show that no matter what code you wrote down, even code I will never see, like just, you know, if there's just only so much code I can see in my lifetime, no matter what you write down, it's just not going to work. It's just not going to solve the problem fast enough. So just from that point of view, it seems designing algorithms is easier. Okay? So somehow lower bounds you have to reason about all possible algorithms. All right? So I assume many of you know about algorithms, so I'll spend some time talking more about lower bounds, at least at the beginning. So the most famous lower bound question, the grandmama of them all, is P equals NP. Okay? And just to give you a very high-level idea of what P and NP are, not to go into definitions, NP is the set of problems where verifying a solution to the problem is easy, and P are the problems where finding a solution is easy to do. Okay? And so by easy, we mean the following technical sense of polynomial time. So there's some algorithm that on inputs of length n runs in some polynomial in n amount of steps. Think of this P of n as n squared or n cubed, you know, something like that. So this is what we mean by easy. You know, most of the things that you see when you're learning algorithms, they're easy. Sorting, easy. Okay? So this problem was articulated in the 1970s by Steve Cook and Dick Karp, and also in the Soviet Union by Leonid Levin. Okay, so rather than going into definitions and things like this, I will just give you an illustration of this. And probably the best illustration of the difference between P and NP is the problem of factoring numbers. Okay. So suppose I give you this number. Okay. It's 232 digits. And I want to know like x and y, so x times y equals this number. Okay. Well, turns out there are two such numbers. Okay. X of this length, y of this length. All right. Now, the problem of given such a number, what are x and y? Right. So this is an NP problem because if I gave you x and y to begin with, if I gave you the solution to the problem, the x and the y, then it's easy to check that x times y equals the given number. You can definitely multiply these things in less than a second on your cell phone. Check, they equal the number. Okay. What about finding the x and y given just this number? What can you do? Well, I give you a very special number here, actually. So this is the RSA 768 number. It took 2 years and a team of number theorists and programmers to find this x and y. A lot of famous people crunched really, really hard to find this x and y, despite the fact that once it's given to me, it takes no time at all to verify the right answer. Okay? So NP is this kind of problem where I give you the number and I want to know the two factors, x and y. But with P, you just, I just want to like find the answer. Okay? So the problem of P equals NP is asking whenever it's possible to check that x times y equals a number, could I do the inverse and figure out x and y efficiently as well? Okay? So this is a very stark contrast between these two kinds of problems. Okay? So P equals NP is asking if verifying a solution to a problem is easy to do, then can we find a solution to the problem also easily? So here's another number. Okay? This one's slightly longer. It's 240 decimal digits. All right? So we actually don't know how to factor this number. Well, okay, as far as we know. Perhaps our friends at the NSA have factored this number a long time ago. Okay, and if you want a bigger list of numbers that we don't know how to factor, there's a whole page in Wikipedia with lots and lots of numbers going up to about 600 digits. Big list of numbers. Okay? So if we could factor integers easily, so this problem, it looks like a simple number theoretic problem, but you probably know that if we could factor these integers easily, then we could break all RSA-based cryptography. So we could break anything that says, it has this little lock here on your web browser. Meh, forget it. It's not really. I mean, it's just crack it open, okay? All HTTPS, SSL, totally broken, okay? These RSA numbers actually is a great resource for someone like me. If someone emails me and say they have a proof of P equals NP, I just forward them this link and say, I'll be waiting. Just all you got to do is just tell me these, short 100-something digit numbers for everything in this list. Okay, then I'll read your paper. Okay. So that makes makes it easy for me, right? Okay. So we believe the answer is no. Okay. I hope this is somewhat convincing. Just this problem of multiplication versus factoring a number. But how could we mathematically prove that? How can we prove that there's just no way to do it? There's no way to break a number into factors. We have to show that some problem that's easy to verify is somehow impossible to efficiently solve. Okay? So this requires us to somehow reason about all easy programs, one way or another. So let me emphasize that P versus NP is only one of many questions of this kind. Many which I simply can't mention in this talk. I just want to mention the most prominent one. But they all sort of hint or at the same kind of thing. Reasoning about efficient computation. We don't know how to do it. Okay. So what are lower bounds good for? So they're impossibility results. Say you can't do something. Well, the first sort of very useful way in which lower bounds are used is for algorithm engineering. So if I prove that a lower bound on a particular mathematical formalization of a problem, it often just means that the way you set up the problem formally is not the right sort of way. I mean, math is just not going to help you if you try for all this. If you wrote the problem down in this way. So you could try something else. You could try to reformulate the problem, go back to it, and see if you can steer yourself away from things which are NP hard and things which are more like P. Okay? But lower bounds have actually been extremely useful in other areas, such as machine learning theory, useful in learning functions for which you know lower bounds for those kinds of functions. For cryptography, as demonstrated with RSA. So you sort of need lower bounds just to get off the ground. You need to be able to say that, you know, I have concocted a problem efficiently, but you can't crack it. You can't, you know, turn around and solve it for me. And also lower bounds come up in an unexpected way in the construction of so-called pseudorandom generators. So these come up when you have a randomized algorithm, an algorithm which tosses coins, and you can argue that, you know, you can mathematically prove that, okay, if you have uniform independent random coins, then this algorithm is going to work well. Well, maybe you know, you can't rely on independent random coins. Well, lower bounds can actually be used to remove the randomness from algorithms. Replace randomized algorithms systematically with something that just uses a purely deterministic sequence of coin flips and still works well. This is a very nice connection and sort of unexpected when you first think about it. But one thing I really want to drive home is that we don't really know what all lower bounds are good for because we have no idea what the proofs of them look like. Okay? I mean, almost all this is just from sort of knowing just that the lower bound holds what you can do. But what if you actually had a mathematical proof, something that actually did the reasoning and you could study it? Then there's no telling what we could learn about computation that way. And so lower bounds, to me, are one of the great scientific mysteries of our time. There are conjectures about them everywhere. Okay? Internet security relies on them being true, but knowing them for sure is mostly inaccessible to us. Okay? So yeah, this is just a great mystery. Why is easy computation so hard to understand? Okay? Why are lower bounds so hard to prove? Why are we so stuck here? So actually, we have a pretty good understanding of why we're stuck. So there are many known no-go theorems in complexity theory with various technical names: relativization, natural proofs, algebraization, so on. What they say in a nutshell is that the common proof techniques that we use are just not going to be enough to prove things much, much weaker than P not equal NP. Things much weaker than this. Just like very simple things we can't prove lower bounds for. And this has caused a great deal of weeping and wailing and gnashing of teeth, a great pessimism in complexity theory. And so the big question here is, how will we make progress? How will we get smarter? How are we going to get off the ground and start really proving that some problems are hard to solve? Okay? So this is what I'm going to try to say something about. Okay? I mean, obviously, I don't have all the answers. But I would like to say something that I hope can be conveyed to everyone. Okay? Well, sort of the main insight in work that I've participated in so far is in connections between algorithms and lower bounds. So we're talking about how algorithm designs have an easier life than lower bound provers. In fact, there are deep connections between the two subjects that we just don't understand yet. We know for sure that they are there. We have sort of glimpses of connections. But there is certainly something more under the hood that we've got to know. And so I'll tell you about the glimpses that we have. So the main idea, I guess the one thing I would like for you to try to take away from this talk is this thing in this box. Designing algorithms is as hard as proving lower bounds, sometimes. Now this is one of those ideas that, depending on who you talk to, is either complete heresy or they thought of it already. Okay, so that means it's a good idea, actually, from my informal judgment. Okay, so yeah, so it's but it's sort of provocative. Or it's very provocative, actually, because the lower bound designer doesn't have it as hard as the algorithm designer. Okay, so somehow the design of certain algorithms is going to actually give you lower bounds. So maybe the algorithm designer doesn't have it so easy after all. It just, they manage to solve other problems. Okay? Or maybe it's just psychological. Maybe we just are wired to think about algorithms in some, more easily than lower bounds, but there's not so much different between them in the end. So here's just my vague attempt to draw some parallel here. So a typical result in algorithm design says, here is an algorithm A that solves some problem on all possible instances of the problem. Now, it's actually amazing how many statements of this form hold. Right? The fact that you can have an algorithm that, say, solves a graph problem on all possible graphs, no matter which graph you see, even graphs you will never be able to see, you can still prove it's going to work and give you the right answer for this graph, okay, on all possible instances. Okay? Now, a typical theorem from lower bounds will say something like, here is a proof P that this problem can't be solved on by all possible algorithms of some class, some weak class of algorithms that I've sort of boxed over here, and I can rule all of them out from solving this problem over here. So what I would like to promote is to draw a parallel between the algorithm here in the algorithm design problem and the proof here in lower bounds, and all possible instances of the problem in the algorithm design problem with all possible algorithms of some class. Okay. So if you think about this, it sort of automatically suggests the kind of algorithms we want to design. So the kind of problems we want to solve are problems which take some kind of algorithm as input itself and perform some computation. Okay? So we want to solve some kind of problem that is taking an algorithm as an input. But we have to be very careful about how we do this. I mean, like if you just took the usual kind of algorithm as input, like the sort of Turing type algorithm, then there are lots of results in undergrad computability theory that just says no matter what you try to do, analyzing the thing is just not going to work. So to make this kind of connection tractable, we have to slightly change the model of the algorithm we're looking at. And this is what I'm going to talk about. Okay. Okay. So at a very high level, here's the specific kind of connection that I'm going to talk about. So suppose there exists some non-trivial circuit analysis algorithm. Okay? So think of this as just some algorithm, some fixed program, maybe a Turing machine, what have you. It receives as input some circuit, encoded in some nice way, some logical circuit. And for all logical circuits, it can do some kind of non-trivial analysis on this thing. Let's say it can determine whether the circuit is satisfiable. In other words, whether the circuit is computing a trivial function or whether it's computing something interesting. Let's suppose it can do this in some nice way, something just better than trying all possible inputs to the circuit and seeing what happens. Okay? If you can set this kind of thing up, if you can solve this kind of algorithm design problem, then you can say there is a function f computable with respect to certain Turing machines for which, for all circuits, they cannot compute this function. For all circuits that cannot compute this function. So you get circuit complexity lower bounds. Okay? So from the design of particular kinds of algorithms problems, ones which take some kind of algorithm or circuit as input and analyzing them non-trivially, you can then prove that for whatever it is I analyze non-trivially, I now have a new function that can't be computed by that. Okay? So this is it's very, very counterintuitive if you look at it in the wrong way. And if you look at it in this quantifier way, maybe it's slightly more intuitive. Okay? All right, but this is the basic kind of connection that I and others have been able to draw, and we've been able to actually prove new lower bounds, new limits on computing using this kind of connection. Okay? So here's an outline for the rest of the talk. I'll give you a very quick introduction to just Boolean circuits and sort of the problems we're thinking about here. I'll compare circuits to algorithms in the usual sense that people learn them. And then I'll talk briefly at the end about how circuit analysis algorithms can imply circuit limitations. Okay? All right. So Boolean circuits look something like this. So this is a Boolean circuit which is taking 3 bits of input. Okay, it's taking the AND of each pair of bits and then taking the OR of those bits. And so it's outputting A and B, or B and C, or A and C. Okay? In general, a circuit of size S for us will take a fixed number of 0, 1 inputs, and it will output, let's say, a single bit. You can generalize it to outputting multiple bits. For us, it's a single bit. Okay? Then for S times, is going to take two previously computed bits, maybe some input bits, such as here, A and B, and compute a function of those two bits. And that will be some new bit that I can use in subsequent computations, such as here I'm taking this OR of things. Okay? So just to give an example, this above circuit on 3 inputs outputs 1 if and only if at least 2 of the inputs are 1. Okay? Now, the size or the complexity of this circuit is going to be like 4 gates in it. And so this is how we can measure computation, but for finite functions. So it's important here that the number of bits of input is something finite. Okay? And then we can talk about, if I want to compute some given function, how many times do I have to take some previously computed bits and get up another bit before I finally get the output of the function I want. Okay? And so trying to minimize this S, the number of little gates you have in here, is the core problem in circuit complexity. All right? So most functions, require humongous circuits. Okay? So a very old theorem of Shannon and matched by Lupinov says that with high probability, if you randomly choose a function by just sort of flipping a bunch of coins, generating a function by coin flipping, this will require a very large circuit, a circuit of nearly size like 2 to the n over n. Okay? So note the number of inputs to this thing. So this is just saying I take a bit, 0, 1, and I take n of those bits, and I output a single bit. Okay? So in fact, every function has a circuit of size about 2 to the n over n. Okay? So just think of it this way. Suppose I'm flipping 2 to the n coins, and I generate some very, very long 2 to the n bit string. Okay? This is just defining some function f. Okay? What this is saying is that there's no way, in general, with high probability, to compress this 2 to the n bit thing into a very small representation. Okay? It's just basically proved by a counting argument. There's just there's too few small circuits and too many randomly chosen functions. So a random one is just not going to be represented by something small. Just a simple incompressibility type argument. So, okay, the universe is littered with these really, really hard functions from the circuit complexity point of view. The question is, which natural functions, ones that we actually want to solve, exhibit this kind of exponential behavior? They require a large number of gates in order to compute them. Okay? So this is a very central question in circuit complexity, just trying to understand which functions can be solved at all. We know that random ones cannot. Can we get? Is there some function of interest, that doesn't have, that we cannot solve with a small circuit? Okay. Right. So that's circuit complexity in a nutshell. So the kinds of things I want to do with circuits is I want to analyze them. So I'm going to talk about computational problems that take a circuit encoded in some way as an input and compute something on that circuit. So the circuit analysis problem is a problem where the input is a circuit. Okay. So here we have some logical circuit written down in some encoding that our program can read. And we want to output some property of the function computed by this circuit. Okay. So we want to know something about what function is it computing inside this little description. So the canonical example of this is a circuit satisfiability problem, also known as circuit SAT. Okay? It's really like the simplest circuit analysis problem in a particular sense. Here you're given a logical circuit C, so you've written down some description of some circuit that's got wired together in some funky way, and you want to know, is it computing the all zeros function? Is it the case that no matter what input I give it, it's always going to print 0? Or is there some input which will make it print 1? Okay? Usually when something makes it print 1, we call it a satisfying assignment, and that's the origin of satisfiability. But we really want to know, is it computing a trivial function or not? Right? So just tell me that. Okay? So circuit SAT is a so-called NP-complete problem, and so it's very unlikely to be solvable efficiently, okay, unless P equals NP. Okay? So probably we're not going to be able to solve this circuit analysis problem very well, but we could ask still if there is some way to solve it faster than the obvious algorithm. What is the obvious algorithm? just try every possible input to the circuit. Okay, so here we're leveraging the fact that there's a finite number of inputs to the circuit. It has a finite number of bits coming in. So you could just, if it's got n bits coming in, there are 2 to the n possibilities. Just try them all, see if any of them make the thing print 1. Okay? So we can ask if there's something faster than this obvious brute force search algorithm. Okay? And maybe this is an interesting question. Maybe it isn't. I always thought it was a very interesting question. Turns out it actually is interesting for other reasons. It actually is connected to circuit complexity. But just the question of, you have a silly algorithm. You have an obvious algorithm. Is it the best you can do? This is just a very fundamental question by itself. Okay. All right. So that's the quick introduction to circuits. Okay. Now I want to talk about how circuits compare to algorithms. Okay. So in the usual algorithmic model, where you think of writing a single program that's going to solve a problem, you have some finite description of some program, and this program can take in arbitrarily long inputs and still solve the problem. Okay? If you give it an input of length 10, no problem. Input of length 1,000, no problem. 1,000,000, no problem. 100,000,000, no problem. This thing always solves the problem. Single thing. Okay? That is in contrast with the circuit model, where we only allowed you to take in fixed length inputs. Okay? So if we're thinking about how algorithms and circuits can relate to one another, we've got to sort of correct this tight mismatch where algorithms can take in arbitrarily long inputs and circuits can only take in fixed length inputs. And there's a very easy way that complexity theorists came up with sort of unifying the two. And the idea is to talk about a computational model called a circuit family. And the circuit family is an infinite collection of circuits, infinitely many. And you have a circuit on 1 bit of input, a circuit on 2 bits of input, a circuit on 10 bits of input. For every possible size of input, you've got a circuit with that many inputs. Okay? So for each n, you have a circuit C sub n that's going to be run on inputs of length n. And so it's obvious what I'm going to do when I want to compute something. You give me an input, I measure its length, I feed it to whatever the circuit is in the collection that matches that length. I run it, it gives me some answer. Okay? That's how the circuit family would compute on some problem that would normally be solved by an algorithm. Okay? All right? So in this model, this circuit family model, programs have infinitely long descriptions a priori. Okay? There is nothing bounding what these circuits could be. You get a separate program every single time your input changes. So it's possible that, if your input is 1,000, there's something really clever you can do just on inputs of length 1,000. And on 1,001, you got to restart everything, do something completely different, and get something very good. Okay? So there's this infinite description can be really, really powerful. Okay? But our notion of efficiency here is this class P-poly. So efficiency for algorithms is just the class P. P-poly is a set of problems solvable with one of these infinite circuit families. So a separate circuit C sub n for each input length, where for every n, the size of the nth circuit is some polynomial in n. Okay? This polynomial is fixed once and for all. Let's say it's n squared. And so this circuit C sub 1,000 will be 1,000 squared size. Something like that. Okay? So this is our notion of efficiency here for this sort of infinite model. Okay? And the idea is that each circuit here is going to be small relative to its input. But you get a separate circuit for each input length. That's sort of the extra thing you get. You get this infinite description. Okay? So this circuit family right here. All right, that's a notion of P-poly. So you may be thinking, programs have infinite length descriptions, huh? Excuse me? Why study this model? Okay, theory dork. That's all fine and good, but why don't you go play off in theory land while the rest of us go change the world? Okay? Okay? Well, I have an answer for you. Okay. All right, okay? So proving limitations on what circuit families can compute is a step towards a non-asymptotic complexity theory. A complexity theory that doesn't talk about polynomials or exponentials or whatever, what have you, talks about numbers. How big does the computation get? if I want to run it on inputs of length 1,000,000? Can I fit it inside the known universe? No. So concrete limitations on computing within the known universe is the thing you would like to have, the sort of the ideal thing you would like to have, something not asymptotic. We don't care about polynomials, exponentials. We just want to know how big is the computation going to get. Okay? So something like any computer solving most instances my 10 to the 4 bit problem needs at least 10 to the 125 bits to be described. Okay? So if you've got this kind of statement, then your problem is just simply not solvable. Period. Okay? So actually, such a statement was proved by Meyer and Stockmeyer in the 70s for a particular logic problem. And they derived it by reverse engineering a circuit lower bound. Because circuit lower bounds are actually explicitly considering the trade-off between the size of an input and the size of the computation you got to throw at the input to solve it. Okay? Whereas P-Zimpi is actually not talking about this. You're talking about a fixed algorithm that's going to work on all inputs. Okay? And so the universe, turns out, stores less than 10 to the 125 bits. This is the famous Bekenstein bound in the 1970s. It's derived from that. And so what you're saying is that any computer solving most instances of my problem just won't fit within the known universe. Okay, that's a pretty good lower bound. Okay, so that's the kind of thing we would like to have. And so circuit family is just some stepping stone to getting some non-asymptotic complexity. Things where we're just talking about numbers. That is the ultimate goal. Okay, we are really, really far, but okay. That's the, okay. All right. So how do algorithms compare to circuit families? Okay. So we define this thing. How does it compare to the uniform one-program Turing model? So if you've got a program that runs in, say, t of n time on inputs of length n, so n squared time, then it's well known that you can always get a circuit family that will do the same thing, and it has about t of n size as well. There's some extra little factors, about t of n size. So you can simulate efficient algorithms with efficient circuit families. Okay? So time will scale with size. All right? So that's all fine and good. In fact, if you flip random coins in your algorithm, and it gives you the right answer with high probability, you will still be able to get an infinite family of circuits. It has about the same size. And so in a sense, you can remove the randomness when you allow for an infinite circuit family. And this is nothing more than the statement, okay, in complexity theory terms, that BPP is in P-poly. Randomized polynomial time has efficient polynomial size circuit families. Okay, okay, suppose I'm just looking at circuit families. I want to know, can they be simulated by algorithms? Well, it turns out there is a family where, in fact, every circuit has size about n. So linear size circuits. So this is definitely in P-poly. There's only a linear size. As the input grows, it only just grows linearly in the terms of size. However, that family has no algorithm at all. Okay? There is just simply no algorithm that will solve the problem that is solved by this circuit family. Okay? So you can't like hope to make them equivalent. Okay? And the main key here is that the circuit family gets an infinite description. You get a different circuit for every input length. And here you have a finite description, a single algorithm running. And this is just a statement that some undecidable problems, in fact, many of them, are in P-poly. Okay? So undecidable meaning there's no algorithm at all. Okay? That's just technical term there. Okay? So finally, I want to talk about, okay, suppose you've got a really complicated algorithm. What can you say about the size of circuit family solving it? So let's suppose I have some algorithm running in exponential time. So 2 to the n steps. So given an n-bit input, it takes 2 to the n steps. So like something just solving the trivial algorithm for circuit size. Something just going through all possibilities to the inputs and just seeing what happens. Okay? So it's actually open. It's an open question whether every exponential time algorithm taking an extraordinary amount of time, can be solved by circuits with a circuit family with n squared size. Every circuit has n squared size. This is a really, really remarkably open question. So is it somehow possible that extremely long time-consuming computation can be split up into infinitely many tiny little chunks where on every single input length, when I solve that problem optimally, I actually get only n squared amount of computation. This is possible. It's actually possible. We don't believe it's true, but it's still a possibility. We cannot rule it out. And this is saying, in complexity terms, that exp in p poly is an open question. So exponential time being in poly-sized circuits is an open question. Okay? So just to give you just a even more crazy way in which we still don't know how, like the power of circuit families, we'll talk about exponential time versus shallow nets. Okay, some of you might have attended MSRI workshop on neural nets. Okay, this is also, we're talking about shallow nets here. So this is going to be very, very shallow neural networks. So suppose you've got an algorithm, and this algorithm is solving a problem that's solvable in so-called non-deterministic exponential time. So this is like some just gigantic, unfathomable class. So this is problems where the solution takes exponentially many bits to describe. And then verifying the solution is exponentially. So this is just some gigantic class of problems. Okay, the solutions themselves are gigantic. And then verifying them takes a gigantic amount of time. Okay, so this is a huge class of problems. Right? So it's actually possible, this gigantic class of problems, every single problem in this class could be, again, simulated by an infinite family of circuits, one for every input length, with the following property. So this is zooming in. Okay. So every circuit looks like the following very, very simple object. Okay. We've got n squared neurons here, so in some layer. We've got n inputs, so this is the nth circuit, so it's going to take n inputs and output a bit. And then from those n squared neurons, they're going to give me a 0 or a 1, and they're going to take one more neuron, some function of those, and output 0 or 1. Okay? So at each neuron, we're just computing some linear form of the input, so there's some weights here being, some real weights being multiplied to 0, 1 values. We're just checking whether that exceeds some particular threshold value, let's say t prime. If it does, we fire. If it doesn't, 1. If it doesn't, we fire 0. It's just this very simple activation function. Okay? So these are neural networks with one hidden layer. Small neural networks with one hidden layer. This should be a very, very weak class. Okay? In fact, if the weights are really small, if the weights are like -1, 1, and 0, we do have very strong lower bound. But if we allow the weights to be anything we want, this is still possible. It's a gigantic gap in our knowledge. Okay? So we don't yet understand very simple neural networks. Okay? Just even things like just one hidden layer. Okay? Just one hidden layer with a simple activation function. We don't yet know. Okay? And so, all right. So I'd like to just give an analogy here of an alien brain versus infinitely many fly brains. Okay. So think of this non-deterministic exponential time thing as you got some super advanced, alien brain. No, think of it as like something times 100 that. Okay, something, just some brain that's solving problems unfathomable to you. Okay? Okay, but it's one brain. It's just one of them. Okay? And then you want to know if there are infinitely many little fly brains, just 2 layers of depth. Infinitely many of them, though, which will also solve the problem, no matter what the big alien brain is. Okay? So the only advantage you have is that there are infinitely many fly brains, and there's a different one for each input length. Is that enough? Almost certainly not. But it's the infinitely many that trips us up. Okay? All right. Okay, so now I want to talk in the remaining time about how circuit analysis algorithms can actually imply circuit limitations. Okay? So circuit analysis algorithms can imply circuit lower bounds in particular situations. And in a particular sense, this was well known a long time ago. There's a theorem of Karp, Lipton, and Meyer from 1980, which says, suppose we had extremely efficient circuit analysis algorithms, like basically perfect circuit analysis algorithms. Okay? So then there are problems solvable by algorithms in exponential time, say 2 to the n time, long amount of time, that cannot be solved with a polynomial-sized circuit family. So this would resolve this x in p poly question we were talking about earlier. Okay, so just a notation, if p equals np, say circuit sat is np, that is a good circuit analysis algorithm. Then we would have This class X was not NP poly. Okay? This is a very interesting implication. Very interesting that an algorithm analysis could, even in P equal NP, okay, it's probably not going to be there, but some algorithm analysis can actually prove a lower bound. Can actually lead to any lower bound at all. Okay? But the thing is, we don't believe the hypothesis is true. So it's kind of like saying, if pigs can fly, then pigs can oink. I mean, like, we don't believe the hypothesis. We expect the conclusion to happen. Okay? So it could be useful, but it seems to be a limited utility. It seems like we have to assume you've got like this amazing like circuit analysis algorithm. Well, let's go study that. I mean, okay, maybe X with P poly, not in P poly happens, but okay, this is by far the more interesting of the two to me. Okay. So what we want to do is take the wings off this dude and bring him back down to earth and like maybe he can like oink a lot. Something that is actually possible, and then maybe we can prove something that we expect anyway. Okay, so a circuit lower bound. Okay, that's what we would like to do. All right, and so we were able to do this in particular restricted situations. So this is work of myself and many others who are working on this too. And at a very high level, what we can say is that a slightly faster algorithm for the circuit SAT problem, just slightly faster than exhaustive search, already implies lower bounds against circuits solving these problems in this gigantic class, non-deterministic exponential time. This class for which it's possible that even neural nets as one hidden layer could just solve the class. Okay. So in pictures, what we're saying is that suppose I give you just some arbitrary circuit, and there's some way to inspect this circuit, and you can find an input which makes it print 1 whenever it exists. Okay? And the one extra thing I want to say is that instead of taking, say, the exponential cost of 2 to the n time, as you would have exhaustively, you take 2 to the n over n to the 10 time. Okay? And you do this for all polynomial-sized circuits. Okay? So let's just say you do this for every circuit in a particular class. You shave off some polynomial. N to the 10 is enough, okay, for our purposes. Supposing you can do that, just a tiny sliver off exhaustive search, then you'll be able to prove for the same circuit class that it cannot compute. Sorry, nx cannot be. So nx is not NP poly. Okay. So what's the intuition behind this? There's two basic intuitions. One is that faster circuit SAT algorithms uncover a weakness in what circuits can do. So in particular, it says at a high level that small circuits can't obfuscate the L0's function. It can't hide it from you. So like, suppose this were a black box, okay? And you can't actually peer inside the circuit and look at what's going on. The only thing you can do is take inputs, stick them in, and get outputs. Let's suppose that's the only thing you could do. And now you want to solve the SAT problem. You want to know there's an input which makes the circuit print 1. All right? Then you can prove that you would need to call this black box at least 2 to the n times to know for sure. Right? There are ways you could trip up any particular strategy for querying this black box, getting inputs and outputs without looking in it, so that you've got to take 2 to the n time. So if we can solve the problem in 2 to the n over n to the 10 time, then there is some fundamental way in which we are opening up the guts of this circuit and getting some advantage over a black box. And it turns out this little advantage, this weakness in circuits that the algorithm has uncovered, is already enough to start proving lower bounds. Okay? All right, so that's the first intuition for why such an implication should even hold. All right? The second intuition is that faster circuit SAT algorithms show a strength of faster than 2 to the n algorithm. So they solve some task that you didn't think could be done, namely find an input which makes the circuit print 1. It does it faster than 2 to the n. Okay? So there's some nice algorithm that can efficiently tell us when a given circuit computes the L0's function. So given these two intuitions, you can think of this problem in general as some kind of game between algorithms and circuits. Okay? There's this circuit SAT problem that algorithms would like to solve, and there are circuits that are inherently devious and trying to fool any given algorithm and wired in some way to keep the algorithm from telling whether it's satisfiable or not. And when we can beat exhaustive search, we are winning the game. The algorithm is winning the game, and no matter what circuit's given, it can somehow drill down through the black box and get the answer. Okay? So with the algorithm winning the game and running less than 2 to the n time, we hope to say circuits are weak, less than 2 to the n time algorithms are strong, and somehow we're going to turn this into some function in non-deterministic exponential time that doesn't have these small circuits. So somehow the circuit set algorithm is showing that circuits are weak, and this theorem is more or less making that formal. Okay? All right. So we can actually apply this kind of theorem to prove lower bounds for restricted classes of circuit C, fancy C. Okay, I won't go into what the definitions of these things are, but the way in which they're proved lays out exactly as you might expect. We show that faster circuit set algorithms for particular classes can imply circuit lower bounds for that particular class. Okay? So just some generic kind of theorem. If C circuits sat on circuits with n inputs can be solved in 2 to the n over n to 10 steps, then this class nx, there's some function, this big class nx, that doesn't have circuits of that kind. Whatever it is that we prove the circuit set algorithm for. Okay? And the second step is just design the algorithms. Now, this is just an unconditional sort of thing. So just we can prove for many interesting circuit classes, ones where we knew no lower bounds whatsoever, we can solve the SAT problem faster than exhaustive search. And then plugging that into the above connection, you get lower bounds for them. So you can improve over exhaustive search in some cases. And so far, this is kind of the only way we know how to prove certain lower bounds, is through the design of the right kind of SAT algorithm. Okay? So this has led to new lower bounds. All right. So I'd like to conclude with the following challenge. So how do we become smarter about computation? So to outsiders, it may seem that we already know maybe too much about computation. Like computers are getting smarter and smarter than us all the time. Yet from the theory level, we actually don't know precisely how powerful they are. Our understanding is really coarse. So the dirty secret, we still don't know too much about the limits of computers. So how can algorithms help prove lower bounds? So this is just in general a direction I would like people to think more about. What kinds of algorithms could help prove lower bounds? Because if we can set things up in this way, then the lower bound problem does not become so intimidating anymore. It just becomes the problem of designing the right kind of algorithm, something that we have done as computer scientists for many years. And then how can lower bounds help design algorithms? I didn't have time at all here to talk about how the connections of that form, but there are many such connections, namely in this thing I briefly mentioned about how lower bounds can imply de-randomization, removing the randomness from algorithms and making them fully deterministic. Okay? But there are many more connections to be found. I'm sure of it. So just earlier this year, my student Brynmore Chapman and I showed that lower bounds, circuit lower bounds, can in a particular sense be equivalent to a particular design problem. So you prove a lower bound, a circuit lower bound, if and only if you design test data for testing whether a given function, a given circuit computes a particular function. Okay? So trying to minimize the test data you need to test whether a circuit computes a function is actually equivalent to proving a lower bound. So this is very nice in the sense that it gives a very constructive way of thinking about how you prove an impossibility result, a very algorithmic way of how you do it. Okay? And so in general, I think we will make serious progress by studying algorithms and complexity as a whole and not as competing fields or anything. We're really doing, I really think we're doing a lot of the same thing, more than we think. Okay, that's all I have to say. Thank you.
We have a question.
Sorry, can you repeat it again? I didn't hear it.
The work of rather than others on how,
Oh,
does that do the same framework, or is it for very different reasons that algorithms and lower bounds?
so like the work of Prasad et al.
Yeah.
Yeah, I mean, so I think what's going on there is they're explaining the fact that, or at least to me, is that proving something is NP hard is actually an algorithm's problem. And so it's like, from my understanding is, either something can be done or it can't be done, and you get a hardness reduction. So I mean, in one case you get an algorithm or you get a hardness reduction. I mean, in both cases you get some kind of algorithm, but I don't know. I mean, are any of them unconditional? I don't know. Are any of the lower bounds you get unconditional?
Well, I didn't mean this specifically. That's why I was referring to the general connection that you talked about.
Yeah.
Algorithms versus lower bounds.
Yeah.
But you're saying this may be a different instance.
I think it's a different kind of instance. It's a very interesting kind of instance, but yeah, I think it's different from what I'm trying to say. But
they do get unconditional bounds on hardness of approximation.
do they? So that's. I didn't think. I thought you still need unique games or a p not equal np or something like this. So I mean, I would like to say something stronger than this. So it's not just algorithm or hardness reduction. Yeah. Yes.
So I have a question about your distinction between family of circuits and
Yes.
algorithms.
Yes.
So in the family of circuits, each one for each size can be totally different.
Yes.
But there is this concept of analytical Kolmogorov complexity, of how difficult it is to describe the family.
Yeah.
And maybe it can give you something in between of this total chaos that each one has its own description and very uniformized algorithm.
Yeah, so that's what makes the problem so immensely difficult, is that it could just be anything. And the hardest cases where each one is sort of incompressible by itself. If they're uniform, if there's an algorithm generating those, then this kind of dichotomy I was talking about becomes a completely different picture. It becomes a very different picture. I mean, there's still interesting questions, many open questions around it, but the picture is very different.
So you said the provocative hypothesis is that lower bound equals algorithm design. This is the...
See, I was very careful not to say that.
No, so I want to say
I'm not trying to say A equals not A or something.
Yeah, then one would say like, oh, but this is very counterintuitive, right? But could you say, maybe it's not that counterintuitive because, for example, at the level of computability, there is some equivalence of computation and proof. How would you say, no, this is
Oh, so, yeah, I mean, even at the undergrad automata theory level, like when I teach them Myhill-Nerode theorem, I say, well, this means that for every language, either it's got a finite automata, it's regular, or there's this weird infinite object called distinguishing set. And this proves that there's no finite automata. And so in that case, it is some sort of constructive way in which you're showing that something is not regular, something does not have a DFA. So yeah, it does come up elsewhere. I only have so much time to talk here. Yeah, that's a good point. Yeah.
So when we're talking about algorithm design, interplaying, lower bounds, we say algorithm design, but then we talk about circuit set.
Yeah.
Most algorithm design people wouldn't think about when they think about algorithm design.
There's a whole community of people that would disagree, but okay. I mean, set solving is quite an enterprise, actually.
So set solving is a big thing.
Yeah.
I mean, like people thinking about like counting independent sets or something.
Yeah.
Are there more kind of fine-grained lower bounds hiding when we have algorithm design for these more kind of conventional problems?
Oh, well, I mean, there are things like if this so-called exponential time hypothesis is false. So then, for example, counting independent sets. If it's in sub-exponential time, you can prove nonlinear circuit size lower bounds. That connection actually carries over in that kind of. So if you could count independent sets in sub-exponential time, you would get some circuit lower bound. It would be even weaker than the ones reported here, but you would get something. There is, the connection still holds over there, but yeah. It would be great to develop stronger connections. I think they're there, it's just very difficult to get your hands around them. Yeah.
Thanks again.